exponential, and logarithmic functions. I promise after that, no more functions. Other things, but not functions. Logarithmic. 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 Okay, these two functions have the most exciting applications. We've seen a lot of exciting applications with medication in the bloodstream of a patient. We looked at height of infants. We had a lot of application. Max min when we throw a ball up and in the air, and so on and so forth. So we have tons of applications. But the applications in this chapter are even more sophisticated, more interesting, in my opinion. So, for example, we are going to look at applications of how fast bacteria grow, or applications of how fast is anything that, let's say, a turkey taken out of the oven and put on the table to cool down. It's going to be a logarithmic function. It will give us the temperature of the turkey in time till it comes down to the temperature, the room temperature. So there are a lot of interesting applications. Bacteria grow exponentially, as I said. Populations like rabbits, rats, birds, fish, they grow. We use an exponential model to represent that growth. What else? Radioactive decay. It's a logarithmic function. It's an exponential function. What else? Say it again. That's exponential. Yeah. Okay. So we're going to look at how much we end up paying, let's say, per month if we take a loan or we deposit money. Let's say we want to put down $50,000 on a home in 5 years. So how much money we should invest today and how in order to get that amount in 5 years, so we can put it down and a down payment on a house. So there are a lot of interesting applications here. But before we get to applications, we have to talk about each function. If you remember, it takes a while. We study the function. We use transformations on the function. We solve equations for both types of functions. And then we're going to look at applications. So we start with exponential function. So 4.1, exponential. The exponential function is what I like to call a friendly function. What do I call friendly and why? Do you remember? It's not important what I call friendly, to be exact. But I call friendly functions that do not give me any headache. I don't have to state restrictions. So this is a function that has domain all real numbers. Friendly function. I don't have to worry about it. So why is it called exponential? It's called exponential because the variable is the exponent. This is a given number. Given number. And it can be, and we have to discuss this is important. Here's a question for you. Can I raise 0 to the third power?
No.
I get 0, so yes, the answer is yes. Can I raise 1 to the fourth power? Yes, so 1 to the fourth power is still 1. Can I raise -2 to the third power? Of course, and I get -8. So all these are possible. However, they are not allowed when it comes to an exponential function. In other words, what I'm saying is the base cannot be 0. This little a cannot be 0, cannot be 1, and cannot be negative. Okay, fine, you told us what it cannot be. Now tell us what it can be. So a can be either a number strictly greater than 1, or it can be a number between 0 and 1. These are the only options. And do you remember when we graphed quadratic function, there were two options, either opening upward or either with a minimum or with a maximum. The same thing here. We're going to look at two different shapes. So one shape will be, can you give me a number greater than 1? Perfect. So 2 to the x will be one shape because the base in this case is greater than 1. And here's another option. Can you give me a number, a positive number, of course, between 0 and 1? And the simplest one to work with will be indeed 1/2. You can choose anything else. So this will be a totally different shape because the base is between 0 and 1. For x squared, it depended on the leading coefficient. If the leading coefficient is positive, x squared has a minimum. If the leading coefficient is negative, x squared had a maximum. Here it's a different story. If the base is greater than 1, it's going to be one shape. If the base is between 0 and 1, a different shape. I don't want to divulge anything yet. Okay, so let's do that. Let's start with graphing this. And then graphing this. And analyze the two. And then look at some transformations. Of course, we can't get away from transformations. So let's say f of x equals 2 to the x. We start with the table. We first analyze this function. Let's learn from it and see what it is all about. And then we'll continue with other things and some applications here as well. What did we say about 2 to the x? A minute ago I said it's friendly. Yeah. Yes, which means the domain is, remember we are trying to graph. So yes, we want to graph 2 to the x. That's our next step. This is what we are trying to do right this moment. Graph 2 to the x. Yes, perfect. It is all real numbers. It's a friendly function. We don't have to worry about it. So now I'm going to pick some small x values like -2, -1, 0, 1, and 2. And I would like us to determine the corresponding y values. So let's take it slowly. So let's plug in -2. When I plug in -2, I get 2 to -2, which is 1/2 squared, which is 1/4. Can anyone now plug in -1 and tell us the answer? Perfect, 1/2. Can anyone plug in 0 now and give us the answer? 1, very good, 1. So let's write this on the side again. A raised to 0 is always 1, except when a is 0. 0 raised to 0 is not 1. If you want to know what that means, you have to take my calculus class. Please. So any number raised to 0 is 1 unless it's 0. Okay, so let's plug in 1 and we get 2. Let's plug in 2 and we get 4. Okay, so now we want to discover the end behavior. We have not done this before with the other functions because there were different functions. There were either polynomial functions or rational functions. We have not done this to determine the end behavior before, but we have to do it now. So I'm going to that direction. 4, 2, 1, 1/2, 1/4, 1/8, 1/16, 1/32, 1/64, 1/128. Where am I going?
Towards 0.
Towards 0, very good. Towards 0, excellent. Now we go this way. 4, 2, 8, 16, 32, 64, 128. Where am I going? Excellent. We have not seen this before. At one end and the other end. What does this mean? When x approaches -infinity, the function values get closer, the function values get closer and closer to 0. What does that mean?
Has a horizontal.
Horizontal asymptote only only at negative infinity, not on both sides. We have never seen this before. So y equals 0, horizontal asymptote at negative infinity only. We are ready to graph this weird function that appears to be insane. No, not at all. Has a horizontal asymptote, but only at one end. We have not seen this before. Okay. I cannot graph a horizontal. I don't even need to because it's the horizontal, it's the y-axis, it's the x-axis. But I cannot graph a horizontal line just on one piece on one side. I have to graph it all the way. So I plot the first point. Can anyone dictate the first point? The first point. Say it again. I already have that. Yes. Perfect. Yes, I agree. Although that's not a point, but yes. Very good. Negative 2 1/4. Next ordered pair. Very good. Next ordered pair. Excellent. Next ordered pair. Excellent. That's good enough. This is the graph of 2 to the x. It's the fastest growing function that we have seen in this class. What can you say about this function? Just anything. What can you say about this function? I can say a lot of things. First of all, I can say that has a range of all real numbers. And I can say that, I'm sorry, has the domain of real numbers, and the range is?
1 to infinity.
So the range is?
1 to infinity.
It has a horizontal asymptote at 0. So we cannot start at 1. 0, 2, very good. So we know that the domain of this function is all real numbers. We know the range is 0 to infinity. Is this function increasing or decreasing on all its domain? Excellent. Is this function 1 to 1? By the? Excellent. Is 1 to 1. Does it have an F inverse? Very good. If it's 1 to 1, it has to have F inverse. I know nothing about F inverse, but I can graph it. When I graph the function and its inverse on the same coordinate system, I must graph y equals x first. Can you give me any ordered pairs that I could use to graph this inverse? Say it again. 1. You said 1?
No, I said 1.
You said 1/4 negative 2. Awesome. Absolutely. Bless you. 1/4 negative 2. Excellent. 4 2. Very good. One zero indeed. That's the key point. Very good. My graph is not perfect, but this is the inverse function of 2 to the x that we're going to talk about shortly. This is the inverse function because the exponential function is 1 to 1. It has an inverse, and this is the graph of the inverse function. And it will definitely have a base greater than 1. In this case, it's 2. 2 is the base. We want to write a equals 2, not 2 equals a. Very good. Thank you. Is there anything else we can say about this function? Does it have y-intercept? Not the inverse. I'm still talking about 2 to the x. Does it have a y-intercept? Perfect. Y-intercept is 0, 1. Does it have an x-intercept?
No.
Very good. Does it have any asymptotes?
Yeah.
Yes. Y equals 0, horizontal asymptote at negative infinity only. Great job. Before we look at the other shape, I would like us to practice with one transformation. Now we are adding 2 to the x to the long list of base functions. Linear, quadratic, square root, cube root, absolute value, x squared, x cubed, the cube root of x. This is the next one on the list, 2 to the x. So I'm going to create a function like f of x equals -2 to x plus 1 and plus 4. We're asked to graph using transformations and determine the x and y-intercepts algebraically. So this is our example. Graph using transformations and find x and y-intercepts algebraically. Graph using transformations and find the x and y-intercepts algebraically. Graph using transformations and find the x and y-intercepts algebraically. Okay, I have to identify the base function, and then 1, 2, and 3. Base function, please. And no, we cannot say the absolute value of x, we cannot say the square root of x, we cannot say x squared or the cube root, but we have to say 2 to the x. We just talked about that. Very good. Perfect. What is the first transformation on 2 to the x in the order of operations? Yes, 2 raised to x plus 1. My 10 fell. Sorry. I touched it and... Okay, what does this do? When we change x into x plus 1. Say it again. Careful. A change in x. A change in x cannot do up and down. A change in x has to do something on the x-axis. Left 1. Perfect. Left 1. Excellent. The next one in line is -2 raised to x plus 1. What does that do to number 1? Exactly. Reflection. With respect to the x-axis. And finally, -2 to x plus 1 plus 4. Since it does not touch x and it touches y, yes, it's up 4. Ready for this? We have to remember the graph of 2 to the x. If we don't remember the graph of 2 to the x, the whole thing fails. We don't know what to do. So how do I graph 2 to the x? It's an increasing function. It has a horizontal asymptote y equals 0. It's an increasing function. It crosses the y-axis at 0, 1. Very good. And it goes to infinity. Perfect. So this is my marker, if you want. The important point. So this is 2 to the x. Then you told me to shift this 1 to the left. Careful, please watch. I'm shifting this point 1 to the left. So therefore, I shift the entire graph. It's not a straight line. This is 2 to x plus 1. The horizontal asymptote doesn't move anywhere because we shifted the graph left and right, or left or right, it doesn't matter. The horizontal asymptote stays as is. Then you asked me to reflect, which is perfect. I have to reflect. Where does this point go, which is at now at -1, 1? Where will that point land if it's reflected with respect to the x-axis? Where does it go? -1, -1. Careful now. So here's the graph. This is the graph of -2 to x plus 1. Then you told me that this graph needed to do what? But I have to move the horizontal asymptote first. So when we graph a function with a horizontal asymptote, but we are doing this or reflection, the horizontal asymptote doesn't move. But when we move the graph with a horizontal asymptote either up or down, we have to move the horizontal asymptote first. So from 0, where will the horizontal asymptote go? To 4. This was 1, 2, 3, 4. This is the new horizontal asymptote, y equals 4, for the function we're graphing. Now I would like you to tell me, where does this point move? So this point moves at 1, 2, 3, 4. So it moves at 3. Is that clear? So this point goes 4 units up. 1, 2, 3, 4. Up here. So here's the new graph and the final graph. Do I know these? Of course not. I have no idea. But this is the final graph, and we're going to determine these. Oops. Final doesn't have 2 L's in it. Sorry about that. So final graph. We're going to determine the x and y-intercepts algebraically in a minute. So this was f of x, -2 to x plus 1 plus 4. Any questions on this? Okay, how do I determine the x-intercepts for any function? The x-intercept. Very good. Y equals 0. So this is -2 to x plus 1 plus 4 equals 0. So yes, very good. Before that, I will ask you, what type of equation is it? It's nothing that we've seen. You cannot say radical, you cannot say quadratic, you cannot say square root or radical, you cannot say absolute value, you cannot say any of the above. We have never seen this before. So what type of equation is it? Say it again. Oh, of course it's an exponential equation. The variable is at the exponent level. It is an exponential equation. The variable is at the exponent level. Perfect. We will move 4 to the other side. Next step. What do you think will the next step be? Say it again. You can do that, but it's not cleaned up yet. You're way ahead of me. I need one more step to clean it up. It's not cleaned up. Say it again.
Divide both sides by 2.
I can't. It has a power. You can't do that. Exactly. To clean it up, I need to do this first. Absolutely. And then, perfect. I have to change 4 into 2 squared. Very good. You cannot cross out or simplify the bases. We can only think. If 2 numbers are equal and they have the same base, what has to happen to their exponents? They have to be the same. Does it make sense? Indeed, if x plus 1 does not equal this, if x plus 1 is the power, does not equal the power on the other side, those 2 numbers will never be the same. So then x is 1. So 1, 0 will be this point. It was not very far, but of course I don't expect my graph to be perfect. So this was the x-intercept, 1, 0. How do we determine the y-intercept? And by the way, congratulations, you solved your first exponential equation. Y-intercept, how do I get it? Very good. I have to find f of 0. Let's find f of 0 together. 0 plus 1. 2 raised to the first power.
No.
Two.
Nice try. Nice try. One more time. 0 plus 1.
1.
2 raised to the first power. No, we haven't multiplied yet. Okay, 2 to the first multiplied by -1 is -2. Indeed, I agree. -2 plus 4. 2. Very good. So 0, comma 2. Let's see how far I was. Oh, quite close. Quite close. By accident. So this is 0, comma 2 is the y-intercept. I didn't think, because we're going to determine them algebraically anyway, so I just showed the shape. Now, can anyone give us the range of this function? Remember what we said about the range of the original function with no transformations in it. What was the range? Right, but this one has a lot of transformations in that. The range cannot be the same. What is the range now? That's it. So the range of this function, it depends. Yep. Yep. Because it has transformations on it. It's a whole different world. It's no longer the base function. It has all sorts of other things in it. Okay. Let's look at the other shape. The other shape was 1/2 raised to x. Let's see how this one looks like. Like with polynomial functions, right? Degree 3 or odd degree, even degree. The same thing here, 2 options. Okay, what is the domain of this function? Yes, we like this function. We like this function. We don't have to think. -2, -1, 0, 1, and 2. So carefully, let's plug in and find those y values so we can plot those points and graph the function. And then we will determine the end behavior as well. When we plug in -2, careful, because a negative power on a fraction will flip the fraction. Okay, let's do this for the first one. 1/2 raised to -2 is 1 over 1/2 squared, which is 1 over 1/4, which is 4. When we plug in -1, what do we get? Exactly. Thank you. When we plug in 0, what do we get? Indeed. When we plug in 1, what do we get? Yes, and when we plug in 2, remember to square the top and square the bottom. 1/4. I'm going that way. 1, 2, 4, 8, 16, 32, 64, 128. Where am I going? Now this way.
0.
Yes. What does this mean? It's a horizontal asymptote at infinity only. The previous one looked like this, right? This one will look like this. Let's graph it. So please remember, the exponential function has 2 options. Okay, the first ordered pair that you want me to plot in order to graph this function. What would you say? Yes. Here it is. The first one is -2, 4, indeed. Next one. -1, 2. Good. All pure exponential functions have to cross at 0, 1. Mandatory. Because when the power is 0, the answer is always 1. No matter what, if they are base functions. This one is anything but a base function. This one has 3 transformations on the base function. That's why it crosses at 2 and it crosses at 1, and it has range between -infinity and 4. It is a totally different story. Way more sophisticated, complicated, if you want to call it. So, but the pure exponential function has to go through this. If it's increasing or decreasing, we don't care. It has to cross at 0, 1. So 1/2 and so on and so forth, good enough. It's getting more and more difficult for me to plot. So this is the graph of 1/2 to the x. And we know a lot of properties of this function. Its domain is all real numbers. Its range is still 0 to infinity. There is no change there. Is this function increasing or decreasing on all its domain? Careful, look at the graph from left to right.
Yeah.
Very good. It's decreasing. Perfect, on all its domain. Is it 1 to 1?
No.
By the
Horizontal.
horizontal line test is 1 to 1. Does it have F inverse?
Yes.
Yes, of course. I want to graph it. When I graph the function and its inverse on the same coordinate system, I have to graph y equals x. Okay, I'm ready. Please give me some ordered pairs so I can graph the inverse. We know nothing about it, but we can graph it already.
-2, 4.
-2, no. 4, -2, I agree. So 2, 3, 4, -2.
2,
I completely agree with 2, -1.
1, 0.
0.
Yes, I completely agree with 1, 0. And remember, where the function crosses y equals x, the inverse function must cross as well. Because all those points are identical, have identical x, identical y. So here's the graph. This is the F inverse with the base 1/2. Okay, in short, I would like to write that the exponential function in any base is defined on all real numbers and has range. You already told me again, so if you'd like to tell me again, what is the range of this function? Regardless of the shape, the range of the exponential function is 0 to infinity. We know nothing about its inverse. We do know the graphs now. But I would like you to identify the domain and range of the inverse. When we get to it, we already have the information. What is the domain of the inverse function? Of course, 0 to infinity. And the range? They are carved in stone. As long as they are inverses of each other, once we establish the domain and range of the function, we know the domain and range of the inverse. There is no discussion there. So what do you realize then? Will I call the inverse function of the exponential, will I call it friendly? No, it's not friendly. It's like the square root has a restriction. It's like the rational function has restrictions. It's not a friendly function. Look at its graph. It only exists between 0 and infinity. Okay, good. So let's look at a quick transformation. Let's say f of x equals 1/2 to x minus 2 plus 1. And this time I'm not going to ask to determine the x and y intercepts algebraically unless you want to. We can. So base function, please. Yes, 1/2 to the x power. 1, transformation 1, and transformation 2. This has only 2 transformations. In order of operations, what would be the next one?
Right.
Yes, 1/2 to x minus 2, which is right 2. Very good. And then an up 1. Perfect.
So,
Yes, please.
so is that like considered like basic? So like basically for the like I don't know what to call it, the exponent, I guess.
Yes?
At the top, are we basically like putting that in parentheses? So that would be like our inside function, basically.
The inner function is x minus 2, and the outer function is 1/2 to the x.
Okay.
I agree completely. Yes. Yeah. You can put in parentheses or not. It's the same thing, but yes.
Okay.
Yes. So we graph 1/2 to the x. Is it increasing on all its domain or decreasing on all its domain? Decreasing because the base is less than 1 and always crossing at 1, 0. So this is the graph of 1/2 to the x. Always decreasing and crossing at 0, 1. Then you told me to shift this right 2. This is our point, basically the only point we need, and we have to shift it 2 to the right. Right now is at 0, 1. Where will it land? If it's at 0, 1 right now, where will it go? Yes? 1. Very good. So this is now the graph of 1/2 to x minus 2. I meant to write. Perfect. So now we want to shift this up 1. But what do I have to shift first? Because these two graphs have a horizontal asymptote of y equals 0. I must shift the horizontal asymptote first. Where?
At 1.
Up 1. Very good. So now the new horizontal asymptote is at 1. And now where does this point? Our marker now is at 2, 1. Where will I shift this point, and then the graph will shift with it? 2 indeed. Perfect. So this is the new graph. And if we are asked, so this is the final, 1/2 to x minus 2 plus 1, and I would like us to identify the range, and then we can look at some applications before we move on. Can anyone give us a range? Very good. It is 1, infinity. Excellent. Thank you.
So,
Yes, please.
so if the coefficient is less than 1, it's decreasing.
The base.
So the base is less.
When
than
the base is less than 1, the function is decreasing. When the base is greater than 1, the function is increasing.
1. Okay.
Okay, so let's look at a more problem. 2 different applications here. Of course, I'll let you choose. Are we interested in the explosion at Chernobyl, or are we interested in the population of, bless you, in the population of India? You want the explosion from Chernobyl? Okay then, Chernobyl it is. Here it is. This book is okay. I can't. Yeah. Okay. In 1986, the explosion at the Chernobyl nuclear plant in the former Soviet Union set about 1,000 kilograms of radioactive cesium-137 into the atmosphere. The function 1,000 times 0.5 raised to x over 30. First of all, what type of function is this? Exponential, because the variable is at the exponent. Very good. Describes the amount f of x in kilograms of cesium-137 remaining in Chernobyl x years after 1986. So I have I have to write down all this information. I have to copy the function. I have to copy what x represents. I have to copy what y represents, or f of x. So let's do that. So this is problem 66 on page 475. And we have f of x equals 1,000. You don't have to put 0.5 in parentheses. You can or cannot. It's fine. But you have to have a raised dot here or parentheses. It's up to you. It says the function describes the amount f of x, take notes, in kilograms, x years after 1986. So what is x for 1986 if x is the number of years after 1986? Say it again. 0. Very good. If even 100 kilograms of cesium-137 remain in Chernobyl's atmosphere, the area is considered unsafe for human habitation. Find f of 80 and determine if Chernobyl will be safe for human habitation in the year 2066. So 80 years since 1986 will be the year 2066. And we have to use the graphing calculator on this. So let's do that. So I didn't use it with the previous class. Okay, so since we only have one variable, one number that we want to plug in, so we put in 1,000 multiplied by 0.5 power, and in parentheses, we will have 80, because that's all we need to do, replace x by 80, divided by 30. And the power has to be in parentheses. For some calculators, for others, we may work without. I'm not going to give you advice. I don't know which calculator you have. So, but I always use parentheses for the power. So, they say if even 100 kilograms of cesium-137 remain in Chernobyl atmosphere, the area is considered unsafe for human habitation. So this is 157.5 kilograms. So f of 80, 157.5 kilograms. What would you tell people who own a place in Chernobyl? You cannot even in 2066 go back. The atmosphere or the radioactive substance cesium-137 is still present in atmosphere. As you notice, something like this kind of event could have not been modeled with any other function but exponential. And the base is less than 1. And yes, it's a decreasing function. But when it will be below 100 kilograms in the atmosphere, we don't know. But it's a decreasing function with the base 1/2, and it's an exponential function. So that was our first example. Second example of an exponential function before we move on. Let me see the time here.